Welcome to this video on the radioactive decay and nuclear radiation exam questions. I'm just going to take you through the multiple choice to begin with and we'll move on from there. So, looking at the first question here, as it says, radioactive nuclei can emit alpha, beta or gamma radiation. Which type of radiation is the most penetrating? Now, you'll remember from previous videos and from the lesson resource that was created that it was very clearly set out which was the most penetrating, which was the most ionising, which had the longest range, shortest range, etc. So which type of radiation is the most penetrating? The answer for that is gamma. Okay, so gamma has an infinite range in air and in a vacuum, and it is the most penetrating. Second question. Which type of radiation is the most ionising? Okay, so the most able to turn atoms, molecules, etc. into ions. And that is the other end of the scale, and that one is alpha. Okay, so alpha, you'll remember, has very low penetrating powers, very low range in general, but it is the most ionising. Okay, so if it's short range, therefore it would be quite dangerous. And then finally, which type of radiation has the longest range in air? The longest range. And as stated already, that is gamma. Okay, so 3 marks are up for grabs there. This next question. So as I said to you, always look, as I said previously, always have a look at this information below and then we'll use the info that we have at the top. So complete the table below to show the number of neutrons and protons in the nuclei. Okay, so this is a question that you could potentially overthink, but when you just think of the fundamentals that we've looked at previously within chemistry and actually within physics, this question should be very straightforward. So we've got our uranium is what we're looking at. So we're looking at uranium-238 and we're looking at thorium-234, and it's asking us what the number of neutrons are and the number of protons. Now, you should remember from previous videos, to work out the number of protons, it's always our atomic number. Okay, so as you can see here for thorium, the answer that they've already given you is 90 protons, while for uranium the answer is 92. Okay, and the number of neutrons, you should still remember how to calculate this, and remember the mass number. Okay, our top numbers is what is in our nucleus. Okay, so our mass number is our nucleus, protons and neutrons. So if we're looking for the number of neutrons for thorium, this is this example here, we need to do the top minus the bottom, the mass number minus the atomic number. Okay, and what that leaves us with, so 234 minus 90 gives us an answer of 144. Okay, so another 2 marks that was up for grabs there. Moving down. And I think people found this a little bit tricky, and I can understand why, so don't worry. I'm going to break it down for you so you can fully understand. So the question is asking you to determine what the count rate of carbon-14 isotope was when the tree died. Okay, when the tree died. Count rate, decays per second is what it needs to be in. So the information that the question has given us, that we've got carbon-14, and it's a radioactive isotope with a half-life of 5,730 years. Okay, so that's going to be important. The half-life is 5,730 years. Then we've got a sample of carbon-14 from a fossilised tree, gives a count rate of 20 decays per second. So again, that's going to be important. 20 decays per second. That's of the fossilised tree. The tree died 17,190 years ago. Again, this is going to be important. We're going to need to use that information. So the tree died 17,190 years ago. The question is asking us to determine what the count rate of the isotope was when the tree died. So it's asking us to go back in time. It's not asking us what it will be, it's asking us what it was. And that's kind of the opposite of what we tend to get with these questions, but still very simple for us to break down. So the first thing is we need to work out how many half-lives there were. Because as it says here, the half-life is 5,730 years. Well, if the tree died 17,190 years ago, we can work out the number of half-lives from here. So what we do is we do 17,190 divided by 5,730, and that gives us an answer of 3. Okay, and that is 3 half-lives. So we know that the count rate has gone down by over 3 half-lives. Okay, now as it says here, a sample of carbon-14 from a fossilized tree, okay, the tree that died and then has become fossilized over many, many, many years, the count rate is 20 decays per second. So what we would normally do, if we were looking towards the future of what the count rate will be eventually, what we would then do is we would half it each time. Difference is here, the question has asked us to go back in time and what the count rate was when the tree died, this many years ago, okay? So what we're going to do, because we're looking for the count rate now is 20 decays per second, but we're trying to find out what it once was. So the way we do that is 20, which is our decays per second, as we've said here. But what we're going to do is we're actually going to times it by 2, times it by 2 again, and times it by 2 again. And the answer ends up being 160. Now let me make some sense of that. The reason it's times by 2 3 times is because we have 3 half-lives. If we had 4 half-lives, we'd have timesed it by 2 again. So 2 times 2 times 2 times 2. The reason it is 2 is normally, if we were going the other way, so we was looking in the future what it would end up being, we would times by 0.5, by 0.5, by 0.5, if we were going towards it, because we'd be doing a half each time and the count rate would go down by half each time. Difference is, this question has asked us to do it the other way around. It's asking us what it was, not what it will be. So in which case we have to do the opposite. So rather than timesing by a half, we're timesing by a double. We're timesing by 2. And that's the reason why we have done that. Okay? So that's the answer to that question there. Hope that makes sense. If not, please do drop me a message or leave comments in the comment section below. Okay, finally, just to finish, a 6 marker. Okay, so this question shouldn't be too difficult. 6 marks up for grabs, and it's a nice one that enables you to pick quite a few marks up in your exam. So the question says, explain how properties of alpha, beta, and gamma radiation affect the level of hazard at different distances. Now, even though it doesn't state them, you should by now understand that that is an alpha. That is a symbol for alpha. That is a symbol for beta, and that is a symbol for gamma. Okay. Now, the way that you need to think about this is to think about what properties they have, and as it clearly states here, the level of hazard at different distances. Okay? So we need to think about what alpha, what beta, what gamma, what their properties are, and actually, at different distances, are those properties more severe or less severe, etc., etc. So what I mean by that, if we're talking about alpha, okay, alpha's properties is that it is the most ionizing, but it's the least penetrating. Beta is mid-ionizing, I'm going to say, so it's in the middle of the 3, mid-ionizing and mid-penetrating. And this is going to be important when we come to talking about the hazard at different distances. And then gamma is the least ionizing, but it's the most penetrating. Okay. Now you will get marks just for stating those things that we've said there. Okay. But we need to say more than that. So at the moment we've talked about the properties, but we haven't said what their level of hazard would be at different distances. So the way we can break this down, we need to think about is if it was short range, long range, or mid range. Okay. So linking these, or just to think about these, if we put range, for example, okay, linking these, if we was at short range, and this is where the link comes, short range, then the most dangerous is alpha. And that would have to be quite a short range, but nonetheless, a short range alpha is the most dangerous. And the reason for that is that ionizing, if something is able to ionize atoms, molecules, parts within our body or anywhere else, it is dangerous. We do not want our body cells, molecules within our body, atoms within our body. We do not want them to be ionized. So if we are too close to alpha, it is very dangerous for us, and therefore that hazard level increases. Then at mid-range, beta is the most dangerous. Okay, so mid-range. Beta is most dangerous. And the reason for this is at mid-range, alpha can't do any damage to us because it hasn't got a long enough range within air. So at mid-range, alpha would have no impact on us, but beta would, and beta is more ionizing than gamma. So although gamma would reach us, it's far less ionizing, whereas beta is more ionizing than gamma, so therefore it is more dangerous. And then finally, at long range, gamma is most dangerous. And the reason again for that, blimey, let me write that again. The reason for that is because beta at long range wouldn't be able to get to us. Therefore, the hazard level would be far lower because it wouldn't actually be able to make it. It wouldn't be able to ionize us because it wouldn't be able to have the range to get to us. So therefore, gamma would then become the most dangerous. Okay, although it is least ionizing, it's the only one that would have the range to be able to cause any hazard. So therefore, it would then become the most dangerous out of the three. Okay, so that's the key information there. Now, what I've stated there will get you high marks. What the mark scheme says for level 3, which is 5 to 6 marks, is relevant points are identified, given in detail, and logically linked to form a clear account. So actually, although we haven't done it in sentence form, this here would be something that would be able to gain you within 5 to 6 marks. Okay, so you can get top marks from listing the answer out as said here. If you have any questions, please drop them in the comments below. If you enjoyed the video, give it a like and let me know. Give me some feedback. Thank you. Bye-bye.